Hello. Welcome to Energy Harvesting and Wireless Power Transfer for RFID and Wireless Sensors with Apostolos Georgiadis. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Techniques Society webcast, which is sponsored by ComSol. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when archived webinar goes up so that you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box on the left side of the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the slide area. You can also go into full screen mode if you desire. Refresh or reload the current page if you encounter any problems. If you're listening over your computer speakers, you may need to adjust the media player volume, or you may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now let's introduce our speaker. Dr. Apostolos Georgiadis was born in Thessaloniki, Greece. He received a PhD degree in electrical engineering from the University of Massachusetts, Amherst, in 2002. He is an associate professor at Heriot-Watt University in Edinburgh, UK. He has been involved for more than 20 years in the field of RF microwave wireless systems, and his research interests include energy harvesting and wireless power transmission, and more recently, inkjet and 3D printed electronics. He serves as an associate editor of the IEEE Journal on RFID, and he is the founder and editor-in-chief of the Wireless Power Transfer Journal by the Cambridge University Press. He is an EU Marie Curie Global Fellow. He has published more than 160 papers in peer-reviewed journals and international conferences. In 2016, his proposal for inkjet or 3D printed millimeter wave systems received the Bell Labs Prize, which was third place among more than 250 proposals, recognizing ideas that, quote, change the game in the field of information and communications technologies. Now it's my pleasure to turn the virtual podium over to Dr. Apostolos Georgiadis for energy harvesting and wireless power transfer for RFID and wireless sensors. Apostolos?
Hello, everyone, and thank you very much for the introduction, and thank you for joining the webinar. Let me start. So my talk will be about energy harvesting technologies and wireless power transfer, and the applications that I'm going to describe are mostly related to RFIDs and wireless sensor network, low profile and low power systems. The outline of my talk is as follows. There is essentially three parts in the presentation. I will give a brief introduction about energy harvesting technologies. My goal is to give you numbers so that we know what kind of power levels or what kind of performance are we talking about, or what do we expect from such technologies. Then I will focus, the second part of the presentation, I will describe the challenges that we have addressed in my group and with my collaborators in the last few years related to these technologies. And finally, I will give some examples about energy autonomous or towards energy autonomous wireless sensors that we have implemented. And throughout the presentation, I will, talk to you about our experience in fabricating or in designing those systems, and hopefully you will find it useful. So here's a little bit of introduction. There is no doubt that, with the advances in 5G communications and the Internet of Things, we're talking about ubiquitous wireless sensor networks. So there's a great deal of applications that are arising, such as monitoring, security, health, or even space, that require sensors that are low power, that are conformal, they have low profile. And what is actually more important is that nowadays, not only electrical parameters, electrical performance parameters are important, but also mechanical properties are required. So there's actually a combination of electrical and mechanical, features that one needs to address. And essentially, we have the opportunity to adapt the manufacturing process to the world we're living in. I'm not going to discuss in this presentation about these new, let's say, manufacturing processes, especially related with 3D and additive manufacturing, but it is very related, and you will see from my slides what I mean. So what is important is that we need to extend the energy autonomy of these sensors. And there are two ways we can do it. One is to minimize the dissipated power, so try to reduce the power consumption or increase the efficiency, the operating efficiency of such sensors. And at the same time, what we can do is actually we can try to harvest power from the environment in order to extend the energy autonomy of these sensors. And another point that is important is that now the effect of all these sensors on the environment is becoming important. When we are talking about installing wireless sensor networks with thousands of sensors, it is important to consider what happens if we need to change the batteries or if we need to go there and collect them when they are not operable. So there is a waste management concern, and towards this concern, energy autonomy and even batteryless operation become very, very important. So, as I promised, let's start with the first part of the presentation. When we talk about energy harvesting tailored to wireless sensors, what kind of power levels we are talking about? So I'm listing here some values that in this table that are not state-of-the-art, but that they are common values that one can obtain buying off-the-shelf components. And for example, if one buys a very low-cost flexible solar cell, roughly 6 by 4 centimeters, which costs maybe $2 or $3, one can harvest up to 60 milliwatts under, on a sunny day in an outdoor scenario. Also, for example, there are commercial products, kinetic vibration energy harvesters, that can easily give you a few tens of milliwatts of power. And in the third line, what you can see is I'm listing the harvested power from a commercial thermo-electric generator, which can give us roughly in the order of 1 milliwatt of power. So you can see this is approximately the amount of powers that we are talking about, given the size concerns of wireless sensors. Okay, and finally, in the last line, I'm listing the electromagnetic energy harvesting, the ambient RF energy harvesting, and you can see that we are talking about values in the order of microwatts. And actually, this is a best-case scenario. So most likely, one can hope to achieve, to obtain power levels in the order of a few hundred nanowatts. Okay, so then many people might ask, why even bother considering electromagnetic energy harvesting, since with the other technologies one can do, or seemingly can do, much better? So the answer, or at least my answer to that, is that first of all, it's very easy. Since we're talking about wireless sensors, it is quite easy. It is quite straightforward to introduce RF energy harvesting capability. So it doesn't cost too much to add this functionality. And the second one is that all of these harvesting technologies are very, very sensitive to the application scenario. So depending on the application scenario, maybe electromagnetic energy harvesting is the best solution. Okay? And before I go into more details, I'm listing here in this table, this is a theoretical work by Professor Starner. I think this was from his PhD thesis back in 1996, where he estimated the total available power from the human body. Okay, so I'm listing two columns. In the middle, you can see the total available power from the body, and on the right, you can see the percentage of this power that can be harvested. And the reason for the difference is that, for example, if we consider body heat, you cannot practically enclose the complete body on a harvester, but you can only try to harvest the heat that comes from, for example, from the head or the neck and so on. So you can only take advantage of a percentage of it. And for example, but what is the important point here? The important point is that the unit now is watts, or a fraction of watts. So it's like hundreds of milliwatts. So it's much, much more than what I showed you in the previous slide. So I'm just leaving this as a motivation because the human body can be actually the source of energy for many, many applications. Okay, so let's go through a little bit on the value on the different technologies, energy harvesting technologies that I mentioned, and I will just give you some numbers of what we can do or what you can find in the market. So solar energy harvesting. For those of you who like to see the state of the art, there is a publication that is a table of the state of the art solar cell efficiency that is periodically published in the journal that I'm listing. I think it's a Wiley journal. So I think twice a year they update those tables. And you can see on the left different solar cell technologies, and you can see their efficiency. Efficiency being the amount of energy, of solar energy that is converted into DC electrical energy. So you can see, for example, that the traditional solar cells, the crystalline solar cells, the state-of-the-art is approximately 27% efficiency. And in the bottom, you can see polymer or dye type solar cells that have an efficiency, a state-of-the-art efficiency on the order of 11%. And this is not bad. And actually, what is important is that those last, polymer type solar cells can be printed. Okay, so we are talking about large-scale manufacturing and low-cost manufacturing. So this is what we can do with solar cells nowadays. What about kinetic or vibration energy harvester? I'm just listing again another table, which is taken from I think again it's from a PhD. It's from the doctorate dissertation of Professor Roundy. Okay, and the reason I'm listing this table is because it's actually very, very motivating to see the different scenarios that one can consider in order to try and harvest energy. So, for example, the movement or the vibration of a refrigerator or of an oven, the vibration of windows that are close to a street, and so on. And what is important here, there's two parameters. So this is what you can take, to remember, that the frequency of those, the frequency of vibration is now in the order of tens to a few hundred hertz. Okay, so it's a very, very low frequency vibration. And the other parameter that is important is the acceleration. Okay, the acceleration amplitude of the vibration. This gives you an amount of how much power, let's say, a measure of how much power is there to harvest. Okay, so the tricky point here is that it's not very easy to design a generic, let's say, harvester that can be applied to different applications because the relative bandwidth of all these frequencies is very large. And then I mentioned there is also thermal energy harvesting, and I'm listing this, and in this slide I'm listing a photo of Marconi's, let's say, room in Villa Grifone in Bologna, in Italy, and the reason I'm listing this is because I wanted to give you an example that we're talking about energy harvesting technologies, but these are generally very old ideas. So most of these ideas have been around for more than 100 years, but now technology gives us the opportunity to implement different and more exciting applications. So for example, you can see on the right, this is a thermo-electric generator that Marconi himself was using to actually charge his capacitors and make his experiment of electromagnetic wave transmission. Okay, so thermoelectric energy harvesting, it is based on the Seebeck effect very, very quickly. So essentially, if you have two different kinds of materials, semiconductor in this case, or metal, semiconductors in this slide, but metals can be used as well, and you have two different contacts that are in different temperatures. Okay, then this generates some voltage. And what is the efficiency, the theoretical limiting efficiency of such thermoelectric generators? The absolute limit is the Carnot efficiency, which is related only to the difference of the temperature values of the two contacts. But then you can find in the literature more complicated expressions that include, the material properties that you are using. The bottom line is that Carnot efficiency is itself quite low, and once you take into account the material properties, the obtained efficiency is even lower. So the bottleneck here is that the efficiencies are very, very low. But let me give you an example, and this is one example of a circuit that we implemented. We try to think what is the element in a wireless sensor that generates the largest amount of heat, and that is usually the power amplifier, okay, which typically have a low or lower efficiency. So then the question that we asked is, can we harvest some of this power? So we placed a commercial thermoelectric generator under the PCB that I show you over there of the amplifier, and we harvested a little bit of power as it was operating. And again, the efficiency is very low. For the scenario that we were considering, the Carnot efficiency was in the order of 2%. The measured efficiency was in the order of 0.1 or 0.2%, but we were still able to harvest a few milliwatts of power. And a few milliwatts of power are sufficient to power sensors. So if we're talking about monitoring the performance of such amplifiers or base stations, that could be a solution that, of energy that comes for free. And of course, there is RF energy harvesting that I mentioned. And just to give you some definition, the key element is the Rectenna. And the Rectenna is simply an antenna and a rectifier. And there are different types of antennas and different types of rectifiers that can be used. What you can see on the right is Dr. Brown, that in Raytheon, many years ago, he patented the Rectenna. And he's holding a helicopter that was powered by a microwave beam. Okay, and if you want to remember some number, what we're talking about is the state of the art approximately is that if we're talking about operation in the UHF range around 900 megahertz, if the input power to the Rectenna is in the order of 10 microwatts, the efficiency is that one can obtain, and by efficiency I mean the percentage of RF power that is converted to DC electrical power, is a little bit higher than 20%, maybe 25% the state of the art now, but this is the number that you should remember. And so can we harvest ambient RF energy? I'm just showing you on the left in red, there are some measurements of ambient RF signals in two locations, at Georgia Tech in Atlanta and at Tokyo. It doesn't really matter which one is which, but what I want you to remember or to realize is that we are talking about energy that is very varying, and that typically, so its amplitude varies a lot. So and also, if you do want to harvest a significant amount of energy, you need to look into a very, very broad bandwidth. We are looking here in the UHF range, but still, I'm showing you spectra from about 100 megahertz up to 700 or 800 megahertz. So this poses a challenge to the circuit designer, okay, as you will see later on. And on the right, there are some measurements that I did in our lab once when we were starting to work on the topic, using measuring the leakage RF power at 2.45 gigahertz from a microwave oven at a distance of about 1 meter, or these are versus this. So we could harvest about 1 microwatt in the best case scenario. Okay, but there's also the possibility of intentionally transmitting power. Okay, so and RF power. In this case, we are talking about wireless power transfer, and I'm listing here some milestones. The main difference is that when you intentionally transmit RF power, then you can actually obtain in your Rectenna very high input power levels that are easily comparable to what I show you in the first slides from solar cells and so on. So this actually increases by a lot the possibilities. So again, it was a very old idea proposed by Tesla. Brown in the 60s, he implemented several scenarios of powering using a microwave beam. At Kyoto University in the 90s, or starting in the 90s and until today, they have made a lot of experiments. You can see in the bottom, there's a little airplane, and you can see the bottom of the airplane in orange is an array of Rectennas, and they were powering this by having a transmitter on top of the car, and they could actually power it, and it could fly. And then suddenly wireless power transfer became really popular with a publication from MIT in 2007 that they didn't use far field, but they used near field resonant magnetic coupling, and they were able to transmit a few tens of watts over a few meters. And an important example of a system that actually is working right now is the online electric vehicle, a bus that is wirelessly charged in the campus of KAIST in Korea. Of course, now we are talking about different power levels. That's why I'm not going to get into details, because I want to focus on wireless sensor networks and RFIDs, but you can see the possibilities. Okay, and let me tell you now about the challenges that we have focused in our work in the recent years. So the first one is actually using multiple technology harvesting, and this is in order to address the varying and intermittent nature of ambient energies. Okay, so solar power is fine, but what happens if you are indoors or if you are in the dark? Okay, and so on. And then what in terms of the circuit design, what are the challenges? I will show you. And finally, we try to address more tailored towards RF energy harvesting. When people think of RF energy harvesting, they think of a CW, continuous wave beam, actually more in wireless power transfer scenarios, being used to power some sensors. But the question we try to answer is there any signal waveform that is better, that can do better in terms of the efficiency? Okay, so let me show you some examples. So the first thing that one can do is to integrate solar cells with antennas. So we can do solar RF energy harvesters. This is not a new idea. It has been used in satellite communications since the 90s or even older, if I'm not sure. But can we apply it? What can we do in terms of wireless sensors? And so this is what we try to address. And what we try to do is, can we use flexible materials to implement? So we use flexible commercial solar cells and flexible substrates, PET, textiles, plastics, paper, and you can see some examples here. And we could, have solar-powered circuits, but with capability of RF energy harvesting as well. And one example, this is a textile solar harvester. The challenge here, I will just give you some highlights. You can see that the solar cell itself has one side that is a ground plate, that is conductive. So in theory, you could place it on top of a conductive part of an antenna, of a radiator, and if you do it carefully and you don't disturb too much the currents, then you don't have a problem. You don't affect the performance of the antenna, and I will show you another example in the next slide. But I think for us, the most difficult part was how to place the DC cables, how do you take the DC output from the solar cell without affecting the antenna? And this is an example. This was a shorted patch antenna, and you can see we connect on the bottom. You can see the vertical screenshot, the cut-through plane. Let's say we used one terminal as the terminal of the antenna, the conductive terminal, and we took the other terminal from the shorted side of the antenna, because this wouldn't affect its performance. And this is another example. You can see on the bottom the S parameter measurement, the input impedance of the antenna. It was a monopole antenna, printed monopole antenna, and we placed a solar cell on top of it. And you can see the simulation and then the measurements with and without the solar cell. So you can see that the effect is not significant. And on the right side, you can see the radiation patterns. So essentially, we have an increase in the cross-polarization pattern, but that was not that important. And then what we also, solar electromagnetic energy harvesters is something that is well known, and there's many examples in the literature, but we thought, okay, can we do something more? Can we integrate thermo-electric generators with an antenna? And you can see on the top left, is a shorted patch antenna on FR4, very low cost substrate, 2.4 gigahertz. And on top of it, we placed a commercial thermoelectric generator, which you can see in the bottom left photograph. And you can see the measurements in the middle, so the impedance measurement and the radiation pattern. So essentially, we were able to to have a good impedance performance. You see there is an additional resonance that I don't have an answer as to why it appeared there, but it's outside the band, so we didn't care too much about it. And then we were able to obtain about 2 dB of gain. And actually the efficiency of the antenna itself was affected mostly by the losses of the FR4 substrate. So we lost about half a dB due to the presence of the thermoelectric generator. So you can also integrate thermoelectric generators with antennas. And finally, very quickly, what we did is we integrated a solar cell on top of the thermoelectric generator. So we can do a solar thermal RF energy harvesting, and these are the results. Okay, so what about modeling? Let me focus now on our RF energy harvesters. So the idea here is we have an antenna irradiating structure, an electromagnetic structure, and we have a nonlinear circuit. So this in itself presents a nice problem for the designer because you have a electromagnetic problem and a nonlinear circuit design. But there is some good theory, and this is what I'm listing here. There is a good theory for loaded scatterers by Mouts and Harrington, but there's more work. This is a classic paper. And then you can connect, let's say, you can link your electromagnetic part of the circuit with a rectifier circuit through some kind of a harmonic balance, for example, simulator. And if you do that, if you simulate it, so you can obtain the RF to DC conversion efficiency. So I'm plotting here several results for different rectifiers, okay, with one or more diodes. And the efficiency curves typically look like this, like the one on the top right. So you can see that what you need to remember is the following. As the input power is very low or reduces, the efficiency reduces a lot. And the reason for this is that your nonlinear device, your diode, is not ideal. So there's a little bit of voltage drop across it, and that means lost power. Okay? As the input power increases, the efficiency increases, but it increases up to a certain point, and then it starts dropping again, and this is because we have reached the breakdown of your device. Okay? And so this is what makes it tricky in terms of the design. So you have to know what kind of power levels you will have at the input in order to optimize your circuit. And another big challenge is what happens after the rectifier? What happens when we what happens in relation to the load that is connected after the rectifier? And this is the plot that is on the bottom right. And you can see that there is an optimum load. And if that load varies, the efficiency varies a lot. So there's a challenge over there. Okay? And finally, there's the question, can we do broadband or shall we do multi-band designs? And the answer to that is, if you know the frequency bands that you are targeting, then you should do a multi-band design. And the reason is that you can design high Q matching networks at these specific frequencies, and you can get a better efficiency. But if you don't know if you don't have a specific frequency target, then you need to do a ultra wideband or a wideband design, and your penalty is efficiency. Okay, and I will talk a little bit about that. The next slide. So here's some examples. You can see in the literature several different types of antennas and different types of rectifiers. So this is a circularly polarized Rectenna, okay, a circular patch and a rectifier. This is a dual linearly polarized Rectenna, a square patch with 2 rectifiers, 1 per linear polarization. And this is a dual band, a dipole kind of antenna, with a dual band matching network. I'm just showing you different possibilities. And then when we talk about multi-band design, actually before I do that, and what I wanted to say is that most of the designs come in the UHF or low microwave range. And there is a simple answer to this. The reason is that there are better propagation, conditions, and that the diodes are cheaper, and so on. They have a better performance, and so on. But there is also a possibility to go towards millimeter waves, and there are some examples of, this is 24 gigahertz, but there's also higher frequency Rectennas, and we can get some efficiency. It's lower, but it can be appreciable. And the advantage here is that you can compensate the loss in the performance of your diodes or of a nonlinear device by including our antenna arrays that are actually very low, that do not take a lot of space because of the frequency. Okay, and this is an example of performance. You can a table of performance of dual band rectifiers or multi-band rectifiers in the literature, and you have efficiency versus power density or versus input power, and you can see as the input power is low, very low efficiency, as the input power increases, the efficiency also increases. Okay, and I mentioned the bandwidth considerations. So if you want to design an ultra-wideband rectifier, what you need to do is you need to go back to your theory, and there's this wonderful theory by Boddy and Fano that they actually found the fundamental limit of what is the minimum reflection coefficient that one can achieve given using a lossless matching network for a given bandwidth. And you can try to apply this in the rectifier. And this is an example that we did for an octave bandwidth Rectenna. And what we did is we used, as you can see, a non-uniform transmission line, printed microstrip transmission line to achieve the broadband matching. And it worked quite well. And there's another example that we did of a decade bandwidth Rectenna. And this was inkjet printed. And of course, as you increase the bandwidth, the efficiency is lower, but you can cover a wider range. Okay, I mentioned also what is important is what comes after the Rectenna. What is the load? I showed you that as the load varies, the efficiency varies. So can we make Rectennas that are insensitive to load and variation primarily, and also potentially for input power variation? And the one possibility is to use what is called a resistance compression network. Okay, and how does this work? You can see on the left a very simple circuit. You need two loads. This is the same load, but you need to have it twice, let's say. And this is a load that varies. And you need two branches, reactive branches, that introduce an opposite phase. And once you connect them in parallel, then you achieve a resistance compression. If you simulate the circuit, what you get is what you see on the right. And on the x-axis, I vary the value of the load resistance, and on the y-axis, you can see the input resistance. So as the load varies from 3 to 1K ohms, the input resistance varies from 50 approximately to 500 ohms. So you have compressed the input load variation, and this you can guess the immediate effect on the rectifier. Okay, so what we did is we designed a dual band rectifier using a dual band resistance compression network. The idea was to actually have this condition of the reactive network at two frequencies, and this is the result. You can see it's essentially you have the load. It branches over two. It separates over two branches, and the rectifier at each branch, and you can see in square with squares the resistance compression network, which is essentially a dual band filter structure, and this is the result. I'm plotting the efficiency versus the load at the two different frequencies, and I'm comparing it with a dual band rectifier without the matching, without the resistance compression network. And you can see that the efficiency stays flatter over a wider load range. At high loads, the efficiency drops, but this is because we are reaching the breakdown voltage of diode, so there is not much you can do. Okay. I also mentioned that we try to answer the question, are there signals that are better than continuous wave signals in order to obtain a high efficiency in rectifiers? And what we saw, and there's more groups that study this, what we saw is that signals with a certain peak to average power ratio may lead to a higher rectifier efficiency depending on the load conditions. Several groups studied multi-signs or multi-tone signals. What we focused in our group is other types of signal, random modulation, white noise, or even catalog signals. And we did an experiment that we compared all of these types of signals with the same average power, but with a different peak to average power ratio. And you can see we compare the CW signal on the right. You can see the square waveform of 4 different signals: a single tone, an OFDM, white noise, and a chaotic signal. And we measure those signals in the lab, and we get a certain peak to average power ratio, the chaotic having the highest peak to average power ratio, okay? And we compare their efficiency, and this is what we got. And what we got actually is the result that we got is that at low input power levels, the signal with the highest peak to average ratio achieved a better efficiency, okay? And the reason is that intuitively one can think that the peaks of power can actually drive your rectifier in a better, biasing condition that generates more DC, whereas the average power is very, very low. And again, if you go to higher power levels, the signal with the high peak to average ratio is the one that loses efficiency first, because you're driving the diode to saturation. Okay? And then what we did is we tried to think of we tried to study the signals a little bit more, because initially we just classified the signals with a peak to average power ratio. But this is just a number. Then there's so much more to it. And I'm showing here on the right an example of what is called the complementary cumulative distribution function of a signal. Okay? And this is actually the probability that the instantaneous power of the signal has a certain value above its average value. Okay, so as you go, the 0 dB at the x-axis is the average value, and as you go towards the right, you are going towards the peak, and the peak has the lowest probability. Okay, but what happens to to the different signals depending on the shape of this curve? Okay, and what we thought is we thought to use a different parameter, what is called the variance of the instantaneous power, and we thought that this actually describes the signals more accurately. And I will just give you an example. I'm not going to go into detail of what I meant. So on the left here, I'm plotting the CCDF of a 4-tone signal in the solid line and of a 64 QAM signal. Okay, those signals have the same peak to average power ratio, which is about 7 dB. Okay, but they have a very different CCDF curve, and therefore they behave differently in terms of the efficiency when they are applied in a rectifier. And this is the result. And you can see actually that the optimum load is different depending on the signal. And this is where one can play. So we can use actually the signal characteristics to tailor the optimum load of the rectifier. Okay? So this concludes a little bit the part of the different challenges that we addressed, and I will give you some examples of circuits that we did. So the first example is we try to do, can we have simple low-cost solar-powered circuits? So we did some solar-powered beacon generator. So it's an active antenna oscillator essentially. It's just an oscillator. On the left, this is on PET substrate, on PET. It's a printed monopole. Okay, and you see the solar cells, and on the right there's a slot, a shorted slot, folded slot antenna on paper, and we could power it with solar cells. Nothing special here, and we could see that they work, and there's some example of some measurements. The reason that this became important to us will be evident in a later slide. So we try to use this as RF signal generators or boosters for RFID scenarios. Okay. Another example that we did is we used the solar electromagnetic energy harvester to power a data logger sensor. And you can see the sensor and you can see the antenna. What I wanted to show is that it's very easy actually to integrate solar cells with the antenna. So this is a slot antenna. It's actually a cavity-backed slot. Okay. And we integrated 2 solar cells on top of it. And you can see the supercapacitor, the giant blue capacitor that we used. Okay, so that's one possibility. The other, and I'm sorry, let me. Okay, and then this is another example of a sensor that was powered by solar or electromagnetic energy harvesting. And again, on the top right, this is another slot antenna. In this case, it's a rectangular shorted slot antenna to obtain circular polarization, and just a small solar cell in the middle of it. And we could power a sensor node by combining light and RF energy harvesting. And in the plot, what you can see, the right plot is just by powering the sensor only by using RF. You can see there are two, let's say, slopes, and the reason is we have a commercial DC-DC converter in the sensor, and it has two different modes. So once you reach 1.5 volts, there's a different circuit that kicks in, a different operating mode that kicks in. And if you have worked in the field, then you know it very well that you really need a minimum power to actually get the started, the cold start of the DC-DC converter. And in our case, it was about minus 13 dBm of RF power, minus 12.6. And then the next plot on the left is by using only solar power. And of course, as you can expect, we had more sunlight, so it was faster to charge. What we are showing is the capacitor voltage, so how we are charging the capacitor. And then if we combine both solar and RF, we get the leftmost plot, so it's even faster, the charging. But then what we did is we did an experiment that we used solar to get over the first circuit jump, so that to have it already operating, and then we remove the light and we use the lower value for the RF signal, close to minus 16 dBm, and you could see that the charging is lower, is slower, but it's still possible. Okay, and so I just have a couple of more slides. Okay, wireless sensor networks, they can operate by energy harvesting, but still we need powers that are relatively high or higher than what RFID needs. And the reason is that RFID technology is based on backscatter communication. And backscatter communication essentially gets rid of a transmitter in your sensor. And how does it work? You can see on the bottom right, you have a radiated signal from a reader device, from an interrogating device. This signal powers your sensor, so it's an RF energy harvesting procedure. And then once the sensor is powered, then it simply switches a transistor. It changes the load of the antenna. Every antenna scatters a percentage of its input power. So if you change the load, you change the amount of energy that is being scattered, and therefore you modulate the scattering. So this is how RFID works, and it's a very low power communication. So what we did is, one idea that we try to address is, can we use different RF sources, like simple RF tones, to power RFID tags without actually needing more readers, let's say. So we took a tag, you can see it. We have the reader, and you can see this is, I don't know if you can read it, it's not read rate, I think there's a mistake. So it's reads per second, okay? And you can see the frequency on the left, the plot on the left. And what we did is we used another tone. We just transmitted another tone, for example, taken from the beacon signals that I showed you. And we could, on a frequency that is slightly different, but very close to the frequency of your reader. And we could see that we could actually increase the read rate. So that can work, actually. And then what we did 7 different experiments. We fixed the frequency, but we increased the power of the tone. And you can see that on the bottom right. And you can see what I show you there in yellow, in red, is us transmitting a second tone at the same frequency of the reader. So you see at some point as we increase the frequency, we actually disturb the communication. But if we are at the frequency that is slightly different, which is the blue curve, then we can get a much better result. And then we said, okay, now instead of doing an additional RF source, we will use a solar cell. So what I did is we took a tag, we made a solar tag, and we took the DC of the solar cell and we converted to RF using an efficient oscillator, and we fed it at the same port of the RFID tag. And we were actually able to improve the performance, get a little bit more range. Okay? And I just have 2 potential future applications. I only mentioned very, very briefly the possibility of using millimeter wave rectennas. And the idea here is that you can extend the concept of RFID into millimeter waves. And why do you want to do this? You want to do this because you have more bandwidth. Okay, and this way you can actually obtain a much higher modulation rate. And this is an example of a very recent publication that we we printed a flexible antenna array, and we used a single transistor device, which is what you can see. And by switching the transistor, we were able to transmit gigabits per second, okay, up to 4 gigabits per second communication. So you can think of RFIDs, but transmitting video signals, for example. Of course, you need more energy than UHF, but still, it's very energy efficient compared to other millimeter wave transceivers. And finally, what I want to talk about is what is called ambient backscattering. So essentially, I told you that in RFIDs, you have a reader device that transmits a CW signal that first powers your tag, and then the tag switches to send back the information. But what we eliminate the need for the reader device. What if we just use ambient signals and we just modulate on top of them? So essentially what we did, this was an idea, I should say, first proposed by the University of Washington, and they did it with the TV signals. And what we did very recently with my student, Spiros Daskalakis, the first author in this paper, so what he did is he considered FM signals, an FM antenna, and he actually started load modulating those signals. He just switched the load of this antenna and using a transmitter that was kilometers away, and we were able actually to get communication for over a few meters. And this is a very low power system. And you can see some results. We were able to actually measure on the bottom right very low bit rates, obviously, 500 bits per second or 2 kilobits per second over 3 to 4 meters. And you can see the measured bit error rates in the lab. Okay, so the next challenge is, can we actually power this using energy harvesting? So this is what we are working on, essentially putting everything together. And with this, I conclude my presentation, and I would like to thank you. And I'm available to answer any questions you may have. So thank you very much.
Wonderful. Thanks a lot, Apostolos. Very interesting topic here. Okay, so now it's time for our question and answer session. And before we start, please remember that you can still submit questions through the Q&A panel, and we'll continue to accept those questions until this is through. Okay, so one question here, and I'll try to paraphrase it. So it kind of seems like you're grouping wireless power transfer in with energy harvesting. Is there any significant distinction between those, or from your perspective, is it one and the same?
Yes, it's actually the fundamental physics behind it are the same, but it's a very different problem. And the reason is that the rectifier, the circuit that converts the RF power to DC electrical power, its efficiency is very dependent on the input power level. Okay, so in the case of energy harvesting, typically you have a very low input power, but in the case of wireless power transfer, typically you have a much higher power level. So then you need to optimize your circuit. So do the impedance matching, or the load considerations for the conditions, for the specific conditions of input power of your application. So the design will be different, actually.
Okay. Let's see here. In an early slide, you showed that for electromagnetic energy densities, it was something on the order of nanowatts of harvestable energy. Was there any frequency range associated with that, or do you recall?
I guess we're talking about RF energy harvesting. I think most of the measurements that we have done in my lab are in the UHF range. So roughly from 100 megahertz FM type signals up to 1 gigahertz mostly, but also a little bit at 2.45 gigahertz. And in this case, these are more or less the amount of power that we have been able to measure or to recover. At 2.45 gigahertz, actually, most of the experiments that we did was with leakage power from microwave ovens, but you can also try with placing your harvester very close to a Wi-Fi, let's say, spot. And there's actually, I can send you, I don't remember off the top of my head, there's also some nice measurements by a group from the University of Washington. You know, in terms of the Wi-Fi signals, you have to be really very close, less than a meter or roughly on a meter distance to get something. And similarly, for the microwave ovens. There is an example, actually, it was unfortunate, but it was published more or less at the same time that we were doing this work of a sensor. Or some people just placed a sensor at the door of a microwave oven, and you can think the scenario of the application is as follows. If the oven is working very well, then leakage is minimum, so there's not enough power for your sensor, and the sensor stays asleep or not operating. But if something goes bad and there's leakage power, then your sensor is powered, and then it can start sending, hey, something is wrong here. And so kind of, you know, I'm trying to consider different applications. But yes, so I hope I'm answering the question.
I believe so, yeah. Okay, here's a fairly recent concept. So does the recent breaking of the Lorentz reciprocity law open up any new territory for energy harvesting? This was a recent report, I believe.
I don't know if I can answer that. This is actually a very good point, and there are several. I hope, like my answer is, I hope that there can be something, but there seems to be a bottleneck, and I don't have an answer specific to that, but I think that could be a way to go, or a way to something to investigate. And another option, I think, is the device itself. So here, at this point, we're just taking whatever devices are available, and we on the market, and diodes or transistors, and we use them as RF to DC converters, as rectifiers. But what if we design specific devices? And now with nanotechnology or those memristive type of devices, there are some, you know, nonlinear characteristics that are different, or that, let's say, what if you can tailor the nonlinear characteristics of the device in order to get a better efficiency, or you know, the some bipolar behavior that they talked about, graphene-based transistors and so on. So yes, I hope there's a lot of fundamental physics or laws that you know, can be broken, or mathematics that can be applied to actually help us get over the bottleneck of the efficiency.
Yeah, the current limitations. All right, but certainly an interesting avenue to explore. Okay, so maybe this is a little bit of an easier question. How useful would tunable matching networks be to improve Rectenna efficiency?
Yes, they are. I think when you think about, when you consider energy harvesting, there is not a lot you can do. And the reason is that, you know, maybe the tunable network is based on, I don't know, varactors or diode, you know, or a circuit that is very, very low power, or even close to passive. But the control feature or the tuning feature will have to dissipate some power. So once you start dissipating power on your matching network itself, then you know, your efficiency will drop. So maybe you cannot really do much. Actually, another good avenue that I've been recently, you know, considering was all these non-Foster type networks, so which is basically an active impedance converter, and you can achieve a very broad bandwidth. But if you are talking about harvesting, you know, powers in the order of 1 microwatt, there's not much you can do. You will just lose your efficiency on your tunable network. But if you can afford a little bit more power, so going into a closer to a wireless power transfer scenario, then the tunable network can be very, very useful, because you can tune to a different band, or you can tune to a different frequency, so you eliminate any reflection losses, for example. And that's one thing over frequency, but then there's another issue that is power. So as you change your input power to your rectifier, the input impedance of your rectifier changes. So your matching changes. So actually, I didn't mention this in the slot. I only talked about the very low power and the very high power regimes that you have either very low efficiency or you have a breakdown. But in the middle, you have some losses because of mismatch. Because as you change the impedance of your rectifier, your circuit was matched at a different level or at a different impedance. And there is where your tunable matching network can be very, very useful. So one application is to extend, let's say, the operating input power range. And there are some actually very nice recent works. I need to look for them, but I can send them if you are interested. But yes, so if you can afford a little bit more power, then the tunable matching network is a very useful thing to do.
Excellent. Yes. Okay. So solar cell power harvesting circuits on the market adjust the IV operating point in order to get maximum power transfer. And so did the tests and experiments that you did with the combination of Rectennas and solar cells, did that include such a circuit?
In the examples that I show you, it did not include, and the reason is again similar to what I said. So this is excellent. The maximum power transfer is a very useful and circuit, but it actually dissipates power. So we wanted to minimize any power losses. But then again, I'm going to the same argument. Once you can afford a little bit more power, then this can help you actually do much better. And we are working on this now, actually implementing a maximum power transfer concept together with the harvester. But you need to minimize the power associated with it, and you have to be able to afford a little bit more input power.
Right. Okay. Okay. So on to the millimeter wave Rectennas that you mentioned. So what are the limits in power, current, et cetera, and efficiency for those structures?
Right. Yes. It's not easy to answer off the top of my head. If you can get a high power, and by high I mean in the order of, let's say, 100 milliwatts, okay, then you can have very good efficiencies. And there are efficiencies that are reported on the order of 60%, I think even up to 50 or 60 gigahertz. There's probably more. There are examples of millimeter wave Rectennas all the way to 90 gigahertz or more. So if you can afford higher power, then you can get 50-60% efficiency, which I think is quite good. The one that I showed you, I don't remember now the value. I think we had about 8 or 10% efficiency for 3 to 5 dBm or so, of input power. So there you have to play with the trade-offs. I think we in our case we only use. Then I think you can take advantage of using a directive transmission and using a larger antenna array. So you can use your antenna gain to compensate for the lower efficiency, so that you can receive a little bit more power. So I think this is the way to go. Larger arrays probably.
Okay, that's perfect. Okay, well, so ladies and gentlemen, I'm afraid we are out of time. There are still plenty of questions in the queue. Sorry we couldn't get to those at this time, but I believe the presenter will follow up on those unanswered questions offline. As we said earlier, this session will be archived on the Society website at mtt.org, and all the registrants will get an email reminder with a website address when it's available. For attendees who would like to receive PDH credits, please follow the link in the webcast view and use the code that's provided on the currently shown or last slide of this presentation. Once again, I'd like to thank very much Dr. Georgiadis for his fantastic presentation, and special thanks to our audience for joining us today. We hope you found today's event valuable and that you return for future IEEE Microwave Theory and Technique Society webcasts. Thank you and have a great day.
Thank you also.